Okay, the last section of chapter 10 deals with formation and reactions of esters and amides. And I would say that this is arguably the most important section of the chapter because it is the most content heavy. Okay, there's a lot of important reactions you need to know from this section. So let's start by figuring out how we make an ester. And it says here the most straightforward way to form an ester is to heat an alcohol. So we heat an alcohol in the presence of a carboxylic acid with an acid catalyst and heat. Well, it's kind of redundant because it said heat here, but anyhow. So here's an example. We take a carboxylic acid, we mix it up with an alcohol or a phenol, and we put it in the presence of acid. So this H plus here, this represents acid, and then we heat it and we end up getting our ester. So we form our ester and we lose water along the way. Now you can see that they've highlighted the hydrogen from the alcohol or phenol and the OH group from the carboxylic acid. Well, if you put that all together, you've got two hydrogens and one oxygen, which is what we need to make water. So when you're forming your ester, all you have to do is remember that you're going to connect the carbonyl carbon with the oxygen of your alcohol or phenol, as you see here, to make your ester. So we call this process, it's got a name, it's called esterification, okay? It was actually discovered by somebody named Fisher. So sometimes it's referred to as Fisher esterification. And so the carbonyl carbon oxygen single bond of the ester group is called the ester linkage. So that means this bond right here is what we call the ester linkage. The ester linkage. The reaction of butanoic acid with ethanol illustrates the esterification reaction. So let's take a look here. I'm going to zoom in a little bit. Here we have our carboxylic acid, butanoic acid, and we have our alcohol, ethyl alcohol. Well, you can see that if we take the hydrogen from our alcohol and the OH group from our carboxylic acid, right? There's two hydrogens and one oxygen, that's going to make water. And so all we have to do to draw our ester is connect the carbonyl carbon to the oxygen of our alcohol, as you can see here, and you get your ester, which in this case is ethyl butanoate. Okay, so we've covered the formation of esters. Well, what about forming an amide? The reaction of an amine with a carboxylic acid normally produces a salt, not an amide. So, for this reason, the preparation of amides requires a more reactive carbonyl functional group like an acid chloride. So, acid chlorides are more reactive than a carboxylic acid. So, here we have our acid chloride, and here we have our amine. And you notice that they highlighted the chlorine from the acid chloride and one of the hydrogens attached to the nitrogen of this amine, because those are going to come together to make HCl. So to draw the structure of your amide, all you have to do is connect the carbonyl carbon with the nitrogen of your amine, and that's what's being done here. So if you're wondering, what is an acid chloride exactly? Well, an acid chloride is just an analog of a carboxylic acid. We just replace the OH group with a Cl group like this. Now, the only time that this reaction is going to work is with a primary or secondary amine. So this reaction will work with a primary or secondary amine. However, it will not work with a tertiary amine, okay? And the reason why is because the nitrogen doesn't have any hydrogen on it. Now here's the specific example they've given us. This is benzoyl chloride, which is an acid chloride. We're reacting it with methylamine, which is a primary amine. You can see that they highlighted the chlorine from the acid chloride and one of the hydrogens from our primary amine. And they did that because those are the atoms that form our HCl. So again, to draw your amide, you connect the carbonyl carbon with the nitrogen of the amine, and there you go. There's your amide. And so in this case, it would be N-methyl because we have a methyl group attached to our nitrogen, N-methyl benzamide. Okay, so let's take a look at an example to practice here. DEET, or NN-diethylmetatoluamide, is one of the few insecticides that is effective in warding off mosquitoes. Complete the following reaction to show the synthesis of DEET, and then below, give the structure of the ester or amide formed in the following reaction. Okay, so in A, we have an acid chloride, and we have our amine. So remember, the chlorine from the acid chloride and the hydrogen attached to the nitrogen, those are going to form HCl. So we can put plus HCl over here. So what we have to do to draw our amide is we're going to connect the carbonyl carbon with the nitrogen of our secondary amine. This is a secondary amine because the nitrogen is attached to two carbon base groups, which are ethyl groups. So let's scribble down our product. We've got our aromatic ring. We've got our CH3 group over here. We have our carbonyl, and then we're going to connect that to the nitrogen. Remember, we've lost the hydrogen that's in the blue circle. So now we're going to have two ethyl groups, one here and one here. And that would be the structure of DEET. And of course, we're going to liberate HCl as well. Now, in the second question, they're asking give the structure of the ester or amide. Well, we can see right away that we're actually going to be forming an ester here. Why? Because we're reacting a carboxylic acid with an alcohol. And we know that when we react carboxylic acids with alcohols, we end up getting an ester. So remember that when you react a carboxylic acid with an alcohol in the presence of acid and heat, you end up losing water. And the water is going to come from the OH, from our carboxylic acid, and the hydrogen from our alcohol. And so we're going to put plus H2O here. And so to draw our ester, we're going to connect the carbonyl carbon with the oxygen of our alcohol. So we're going to end up with CH3, then we have our carbonyl, then we're going to have our oxygen attached to our CH3 group. And so we'd call this compound methyl acetate. Methyl acetate. You could also call it methyl ethanoate. That would be a perfectly acceptable name as well. But chemists really like to use common names, so I'll just leave it as methyl acetate. Well, now that we've learned how to make an ester, let's talk about how you break it apart or hydrolyze it. So hydrolysis of an ester is nothing more than breaking it apart. All right. And so ester hydrolysis is the reaction of an ester with water to break the ester linkage. Remember, the ester linkage was the bond between the carbonyl carbon and the oxygen of the alcohol. And when we break that ester linkage, we're going to regenerate an alcohol and a carboxylic acid. And so if you're looking at this and saying, well, this is just the opposite of esterification, you'd be 100% correct. That's all it is. The strong acids are frequently used as catalysts to hydrolyze esters. And when an ester linkage breaks during hydrolysis, the components of water are attached to the ester fragments to form the carboxylic acid and alcohol. So you can see in this example here on top, the general reaction that we break the ester linkage, but then what we're going to do is we are going to attach the OH from our water to the carbonyl carbon that I had highlighted in yellow, and you're going to attach this H to the oxygen of your alcohol. So here's a specific example where we take ethyl acetate and we treat it with water in the presence of acid. Remember, this is just water, and this is acid. And so we end up breaking the ester linkage right here. On the carbonyl, we add our hydroxyl to get our carboxylic acid, which is acetic acid. And on this portion, we add a proton to give us ethyl alcohol. Well, we learned how to make an ester and then break it apart, which we call hydrolysis. We learned how to make an amide, so let's talk about how you hydrolyze or break an amide apart. Amide hydrolysis requires the presence of a strong acid or a strong base, and the nature of the final products depends on which one you use. So what that means is whether you decide to use strong acid or strong base, you're going to end up with slightly different products. And so what they're telling us here is that when you do amide hydrolysis under acidic conditions, you end up with the salt of the amine along with the carboxylic acid. Whereas when you do the hydrolysis under base conditions, you end up with the salt of the carboxylic acid and the amine. So here are some examples. First, we're going to start with acid hydrolysis. Then we're going to take a look at base hydrolysis. So the general reaction for acid hydrolysis is going to cleave the linkage between the carboxylic acid portion and the amine portion. And our carboxylic acid is going to end up as a carboxylic acid, but the amine portion, this portion here, is going to end up as a salt. So we see the example of acetamide here reacting with water in the presence of acid. So we see that the acetyl group gains an OH and becomes acetic acid, but the amino portion here ends up gaining a proton and then reacting with HCl to give us the ammonium chloride salt. Now below we have the hydrolysis and base. And so again, we're going to break that same linkage between the carbonyl carbon and the nitrogen, but this time we're going to get the amine. So you're going to get the amine that comes from the amino portion here, and you're going to end up with a carboxylate salt as is shown here. And the example that they're showing at the bottom is N-methylacetamide treated with sodium hydroxide, which is a strong base. In the presence of heat, we end up with sodium acetate, and don't forget, you're going to get your amine that comes from this portion of the molecule. And so in this case, it would be methylamine. Okay, when aspirin enters the stomach, a hydrolysis reaction takes place. Give the structure of the products formed in the following reaction. So in the first one, we have aspirin being treated with water in the presence of acid. And so that's going to be an ester hydrolysis. And so what we're going to end up doing is we're going to cleave or break or hydrolyze the ester linkage here. And so we're going to get our alcohol, which is going to have the aromatic ring attached to it. So we're not going to touch this carboxyl group here. And we're going to have our OH here from our alcohol. And then the acid that we're going to form is going to be this, which would be acetic acid. So we end up with acetic acid, and this would be ortho hydroxy benzoic acid would be the name of the other compound. So I'll just move this over here. And in the bottom one, we're hydrolyzing this amide with base. And so we're going to break the bond between the carbonyl carbon and the nitrogen. But instead of getting a carboxylic acid, we're going to get a carboxylate, and we're going to get the free amine. So our free amine is going to be this para-hydroxy aniline. And then the carboxylate is going to look like this. It's going to be a sodium salt because we're using sodium hydroxide. So you're going to end up with sodium acetate. And so make sure you know how to do a hydrolysis of an amide in acid or in base. Amide hydrolysis that we just looked at is a central reaction in the digestion of proteins and the breakdown of proteins within cells. However, most amide hydrolysis in the body is catalyzed by enzymes rather than by strong acids and bases. Because of their physiological properties, a number of amides play valuable roles in medicine. The table shown here, Table 10.6, lists some of these important compounds. So we see we have thiopental, and we can see that we have an amide here and another one here, and that's used as an anesthetic. The next compound is amytal or amobarbital, and again, you can see you have an amide here, you have an amide here, and it kind of looks like you have an amide here, but anyhow. And so that's used for the treatment of insomnia. The last compound is an antibiotic. It's ampicillin, and you can see that we have an amide here in the compound. And so if you start looking around at prescription drugs, you'll notice that many of them will have amides in their structure. Okay, now we're going to look at saponification. We've already covered the acid hydrolysis of an ester, which doesn't have any specific name. It's just called the hydrolysis of an ester in acid. But when we hydrolyze an ester in base, it's got a name. It's called saponification. And the reason why we use the word saponification is because it is the reaction that was used all the way back from the pioneers to make soap. They would take animal fat, which is a triglyceride, they'd treat it with base or lye that they would get from ashes from their fires, and they would make a carboxylate salt, which is what soap is essentially. So, saponification, um, it says here, unlike ester hydrolysis, saponification is done in solutions containing strong bases like potassium or sodium hydroxide. So again, the first hydrolysis that we looked at was done in acid, but again, saponification is done in what? It's done in base, okay, in strong base. And so instead of ending up with a carboxylic acid, we end up with a carboxylate salt. If we look at the general reaction that's shown here, you have your ester, and you're going to break that ester linkage with your sodium hydroxide, but instead of getting a carboxylic acid, you're going to get a carboxylate salt. This one is, of course, a sodium salt because we're using sodium hydroxide. And then you end up with your alcohol. The example that they're showing here on the bottom is methyl benzoate being undergoing saponification with sodium hydroxide so that we end up with sodium benzoate. And of course, from our CH3O, we get CH3OH, which is methanol or methyl alcohol. Example 10.11, the ester pentyl ethanoate gives rise to the odor of bananas. Give structural formulas for the products of the following saponification reaction. So we're taking pentyl ethanoate and we're treating it with sodium hydroxide. And so this is obviously a saponification reaction. So what we're going to do is we're going to break that ester linkage, but instead of getting the carboxylic acid, acetic acid from the carboxylic acid portion, we're going to get a carboxylate. So let's draw that carboxylate. It would be this plus our oxygen with a negative charge, and sodium is going to be the cation because we're using sodium hydroxide. So this would be sodium acetate. And of course, we're going to get our alcohol, which has a total of 1, 2, 3, 4, 5 carbons in it total. So that would be 1 pentanol. And so we'll scribble down our 1 pentanol. I want to make sure I have the right number of carbons here. Now they used a condensed structure. I put the whole thing here. So this would be 1 pentanol. And those are the products of this saponification reaction. And so to summarize chapter 10, by now you should be able to classify carbonyl compounds as aldehydes and ketones. You should be able to identify some specific uses for aldehydes and ketones. You should be able to give IUPAC names for aldehydes and ketones. You should be able to talk a little bit about intermolecular forces, what we call IMFs, intermolecular forces, and how they influence the physical properties of aldehydes and ketones, physical properties like melting points and boiling points. You should be able to predict the products of hydrogenation, oxidation, reduction, and hydration, reactions of aldehydes and ketones. You should be able to name a carboxylic acid using IUPAC nomenclature rules. You should be able to name a carboxylate salt, like we saw in the previous problem, sodium acetate, so on and so forth. You should be able to describe some uses for carboxylate salts, explain how hydrogen bonding affects physical properties of carboxylic acids. This is why carboxylic acids have such high boiling points. You should be able to write key acid-base reactions of carboxylic acids. You should be able to name some esters and amides, talk about hydrogen bonding and how that affects the physical properties of esters and amides. You should be able to do hydrolysis of esters and amides in acid or base, and you should be able to write out the reaction of saponification, which is the hydrolysis of an ester in base.